Multiplying matrices. Now, before we multiply matrices, we have two different sets of rows and columns. There are some things we can and cannot do. And let me show you how. We can multiply matrices where they have the same number of columns. These are square matrices, for example. A 2 by 2 can be multiplied by 2 by 2. A 3 by 2 can be multiplied by 2 by 3. Notice the inversion here. 2 by 3 and 3 by 3. We can multiply 1 by 3 by 3 by 1. If the numbers aren't inverted but they're the same, we can multiply those as well. Now I'll explain how to multiply in a moment. But these are not inverted. This 2 by 3 here is not inverted of 3 by 3. We can now multiply 2 by 2 by 3 by 3. And we can add a 2 by 3 to 2 by 3, but we can't multiply it. They either have to have the same numbers, and really what it gets right down to is when we invert one from the other, are they the same? I invert 2 by 2, and I inverted that still is 2 by 2. 3 by 2 inverted is 2 by 3. This one is not inverted, and 2 by 3 inverted is not 2 by 3. So we got to be able to invert it and get the same resulting answer. Because what we're going to do is we're going to multiply the row by the column. And let me take my time in doing this here. We're going to go through one. That's why there's several slides here, but it's really not that hard at all. But we have to be careful. It's not really something you can do in your head. You have to write these down. I've got a 2 by 2 matrix here. 2 rows, 2 columns here. And I got two rows, 2 columns here. So I can multiply this together. Now let me erase this because I'm sure what I'm going to do. What I've done here is I'm going to multiply the first row of this first matrix by the first column of this matrix. And be consistent with this. 2 times 1 goes right here. And then 3 times 6 goes right here. That's the first row, and this 2 by 2 matrix multiplied by the second. The first row of the first matrix multiplied by the first column of the second matrix. I'm going to add these two together. 2 times 1 is 2. So I got 2 right here. And then 3 times 6 is 18. And 18 plus 2 is 20. Let's go to the next slide. I'm going to do I'm still in the first row, but now I'm hitting the second column on the second matrix. 2 times 4 is 8. It's right here. And then 3 times 5 is 15. So 2 times 4 is 8. 3 times 5 is 15. I'm going to add those together. 8 plus 15 gives me the 23. We got our 20 before. Now I got 23. Now I'm going to go to this. I've gone all the way, do everything I can to multiply the first row by both columns. Now I'm going to start with the second row and multiply by the first column in the set matrix. 1 times 1 is 1. 2 times 6 is 12. And that's 1 plus 12 gives me 13. Now guess what we're going to do? We're going to do the second row as we did before. And then the second column. 1 times 4 is 4. Right here. And then 2 times 5 is 10. And 4 plus 10 is 14. So in the end, when I multiply this matrix by this matrix, this is my resulting answer. Now, I'm not going to go through every one of these because I know you'd be bored to tears. This is also in Canvas on our PowerPoint slide. But I just want to take I want to go through just a couple steps here. Those are all question marks. But what's interesting, I want to point out here, you see now why we have to have inversion of the rows columns. This is a 3 by 2 matrix right here. And the second one is a 2 by 3 matrix. So I said, as I learned a little while ago, I can multiply these two together. But notice our final answer will have the same order of rows and columns as the first matrix. So let's do the first row of the first matrix by the first column. 2 times 2 is 4. Here's my 2 by 2. 5 times 2 is 10. So there's my first one. First row, second column. 2 times 4 is 8. 5 times 6 is 30. And 30 plus 8 is 38. So I got 14 and 38. Now I'm going to do the first row. Didn't circle it here. First row times the third column. 2 times 7 is 14. And then 5 times 3 is 15. And 17 plus 14, not 17, 14 plus 15 is 29. Now I've gone through every possible column I can multiply the first row with. And notice they're consistent. But when I run out of one, I run out of the other. 1 times 2 is 2. 5 times 2 is 10. And 2 plus 10 is 12. So on the second row, now the second column, 1 times 4 is 4. 5 times 6 is 30. And that's going to be 34. Second row, third column, 1 times 7 is 7. 3 times 5 is 15. And that's 15 plus 7, which is 22. So we've gone all the way through that. We've done everything in the first row. We have done everything in the second row, all three columns. Now we do the third row through the first column. 4 times 2 is 8. And 3 times 2 is 6. 8 plus 6 is 14. Third row, second column. 4 times 4 is 16. 3 times 6 is 18, which is 34. Third row, third column. 4 times 7 is 28. 3 times 3 is 9. 3 plus 9 is 37. So we multiply these two matrices together. This is our resulting matrix. Do another one here. Can I do it with 2 by 2? Yeah, because if I got 2 by 2 here, and if I inverse the rows and columns, the second one, I still get the same answer to match up. 4 times 4 is 16. 2 times negative 3 is negative 6. 16 minus 6 is 10. First row, second column, 4 times 4 is 16. 2 times 2 is 4. 16 plus 4 is 20. Second, I've touched every column I can in my first row. On my second row, 8 times 4 is 32. 8 times negative 3 is negative 24. 32 minus 24 is 8. And then second row times second column, 8 times 4 is 32. 8 times 8 times 4 is 32. And then 8 times 2 is 16. 32 plus 16 is 48. So there is my final answer. Now, this is some interesting things. We can talk about animation and CGI. When we put it in computers to actually animate things via computer with X, Y's, and C's, we want to use some of these. We talked about some identity matrices, and I want to show you something here. We have an identity matrix, a 2 by 2. Notice it's 1, 1, and 0, 0. A 3 by 3, 1, 1, 1, right here. Everything else is zeros. Here's a 4 by 4 going up to the left, down to the right. Everything else is zeros. And the reason I do this, when I multiply this whole matrix out, if I multiply, and I'm showing you step by step here, But I won't go through every one of them here. But let's just do the first row and first column. 3 times 3, 5, and 7 times 1, 0, 0. I get 3 times 1 is 1, 5 times 0 is 0, 7 times 0 is 0. I go through all these. When I put all this together, this is my answer. And notice it's the same thing, which I got this arrow right here for. It's the same as my answer. And this is an identity matrix. You always saw identity matrix because it has all zeros. It's a square matrix, by the way. And if I had 5 by 5, it'd be 1, 2, 3, 4, 5. And it would look like this: 2, 3, 4, 5. And have all zeros everywhere else. And I'm not going to try to master this right now, but everything else is going to be zeros, except for that row going from the upper right to the lower left. That is an identity. Now, we were talking about vectors a few days ago. We can do geometric transformations with matrices. And actually, this is, we're also using complex numbers to find the conjugate, if you remember. That's what we're looking at here. We can reflect this. We got a vector right here, vector B. If I want to reflect it off the x-axis, that vector B prime here, I can multiply across the x-axis. This is similar, look at this. This is similar to identity matrix, which is one, if it's a 2 by 2 identity matrix, look like this. Except notice, this is -1. Now when I multiply this all out, I get this right here. This -1 brings it across the x-axis. It reflects it, gives me the conjugate. So this is a reflection made across the x-axis matrix identity. I can go across the y-axis as well. Notice, very similar to my original identity matrix. Oops, let me erase that. Try check mark. We don't want that. Try again here. But instead of that negative being on the 2 element, it's on the 1 element right here. And that takes this, we multiply go across the y-axis, my original, my vector. It does this. It goes across the other axis. I want to notice what I've done here. Now, if I had a column vector, normally I'd write 4, 7, just 2 rows, 1 column. But again, I also taught you that we can only multiply matrices by if we can invert it. So what I have to do here is I have to turn this into a 2 by 2 matrix. I just put zeros right here. Here's my x, here's my y. And really what I'm doing at here, this is where it ends up. Here is my 4, 7, and I really should put parentheses or angle its coordinate. And what's the other one? 0, comma, 0, x and y. And that's why I've done this right here. When I multiply it all out, it flips it across the y-axis. I can even reflect along the origin right here. And instead of 1, 0, oops, that's a 1, 1, 1, 0, 0. Notice I've put negatives on both of those. And all this does, here's my vector B. Here's my vector B prime. It is crossing across the origin, which is y equals x. And notice this is -1 here. And what is this slope? It's a slope of -1. We can also go reflection across the xy axis here. And this is interesting. It's interesting when these matrices, especially when we can computerize it fairly quickly here. Now, like I said, original identity matrix for a 2 by 2 is 1, 0, 1, 0 this way, right, right there. But notice what I've done here. Look at this. If I want to reflect across the XY axis, I really kind of throw everything in the opposite direction, which makes sense. I make it 0, 1, 1, 0. And it reflects, here's my B prime right there. And by multiplying by 1, 0, 0, 1, 1, 0 right here, which I've done right here, it reflects it across the XY axis here, or Y, I should say Y equals X axis. Now, what I can do here, I can also solve systems of equations using matrices. And these are just equations we saw in algebra. 3x minus 5y equals 1. I've actually drawn it out here. And then x plus 2y equals 4. And yeah, I can look at this. I can solve this by finding a common equation. So finding an x or a y, subtracting one out, and then putting back in the resulting number, and I end up getting x is 2 right there, and y equals 1. But we always won't be able to draw here. And here's my x is 2 and y equals 1. I solved the old-fashioned way. But can I solve this as a system of equations? Now, I want to show you how this is done. You're not going to be quizzed or tested on it, but you can do this in Microsoft Excel, which I may make a separate video for that actually. You just have to input the video. Input the numbers that determines a matrix, and then from there we go on to develop this. And this makes life a lot easier, especially when you have multiple variables, X, Y, Z. You got 8. You got 26 different variables. You got 50 different equations with a matrix you put together. Now, as I said, what we're looking at here, I got x plus 2y equals 4, and then 3x minus 5y equals 1. Here's my 1x plus 2y equals 4. And then 3x minus 5y equals 1. Notice I put this in the second column here. And here's my x and y. You're going to see why I put this together in a minute. So what I'm doing is I've got my equation here, my a times my x equals b. And I'm representing these matrices as components of an algebraic equation. Here's my a, and multiply times x, which is each by xy. I could have made this q or z, but xy, and I get a resulting b. So ax equals b. And if ax equals b, then x equals b over a. In other words, my answers here, whatever my answer, my 0, 0, 4, let me try this again, 0, 0, 4, 1, divided by 1, 3, 2, negative 5 is going to give me what my x and y are. You're saying, okay, but how do I do this? What we're really doing here, and let me erase this here, because all we're doing is putting, that's worse. Sorry. All we're really doing is rewriting this equation with matrices. Let me erase some more of this stuff. Again, here's my matrix. I'm trying to find my variables, which I'm calling big X here. And that gives my result. And that's A times X equals B. So my X, my variables that I'm looking for, my X and Y, are going to equal B, if I rewrite this, B over A. And here is my A, here is my B, and so whatever this is, I could rewrite this as a fraction. 0, 0, 4, 1 times 1, 3, 2, -5. Well, saying, okay, so that's a matrix. And I remember I multiply this by the inverse. If I had 1 over 2, that's the same. All right, let's make it something different here. Let's make it 3x over 8 equals 1. Well, I multiply both sides times 8. Now cross that off. So we're left with 3x equals 8, and x would equal 8/3. How do I do that in a matrix? How do I find the inverse of a matrix? And that's what we're going to show you. Because if I have you're saying this is a bit hard for just two variables, two equations, but to set up, can you imagine we could do 20 variables, 50 equations, which you're going to see in the real world sometimes. You're looking at different chemicals, different different forms of radiation simultaneously coming in, different types of bacteria growth and decay. So we look at this, and what we need to find is the determinant. And that basically, remember what I said here, if x equals b over a, that's the same as I got to find 1 over a. And that is going to be, what is 1 over this matrix here? 1, 3, 2, -5. I don't want 1 over. I need to find the actual inverse of that. And this is what we're going to do. To find the inverse of that, and that's really called the determinant. Well, you notice what we're doing here. And we've done some algebraic things with this before. Notice what happens is these two switch. The 1 and -5 here. 1, 1, and 2, 2, those are elements here, switch. 1 goes to -5 position, 5 goes to -1 position, which is done right here. And then these two switch, but become negative. So if I had 2 here and 3 here, no, they don't switch, I'm sorry. They become negative. They stay in the same position, but they become negative. Now that I've got this, I need to, and you showed the other part. I wanted to show you that first because it's the easier part. So let's go through, let me go through the other part here. I need to find, that's how I've inversed the matrix, but I need to find, well, the other part of the determinant. And that is found by doing this. It's AD minus 1 over AD minus BC. This is, consider this, AD is A, B, C, D. So AD, 1 times -5 right here, minus 2 times 3 right here. And 1 times -5 is -5, minus 2 times 3, which is minus 6. So it's -1/11. So what I've done here is I have found for the inverse of A, it is simply finding the determinant right here, and then finding the inverse of the original matrix. That's what I've done here. So here it is right here. And if you look, what do we have here? We have a scalar. It's negative 1/11th. Determinant is actually a scalar. So it's going to be negative 1/11th times our new rearranged matrix, our inverse of the matrix, times, and here's my answer, 0041. I'm sorry, I say 0401. So let's multiply this all together. Negative 5 times 0 is 0. First row, second column. Negative 2 times 0 is 0. There's the first one. Erasing all this here. Now let's do the first row, second column. Negative 5 times 4 is negative 20. Negative 2 times 1 is negative 2. That's negative 22 right there. So we got 0 and 22. Now let's do the second row, first column. And that is going to be negative 3 times 0 and negative 1 times 0. That's 0, 0. And then negative second row, second column, negative 3 times 4 is negative 12. 1 times 1 is 1. That is negative 11. Still got to multiply by the scalar out here, that determinant. And when I do that, this is negative 1/11 times 0 is 0. Negative 1/11 is 0 is 0. Negative 1/11 times negative 22 is negative 22 over negative 11, which is 2. Negative 1/11 times negative 11 is negative 11 over negative 11 is 1. So look, I have my answer. My x is 2, my y is 1, as we solved before the traditional way. Now, I know you're thinking, yeah, but this takes so long. And this is how we do it. But you can do the same thing with if you have 3 variables, x, y, and z. If you have 5 equations and 10 variables, that's the wonderful thing about this, because it gets harder and harder after you have 2. We can do 3, and that takes a while as we learn in algebra. If you start doing 15 and 20 with 6, 8, 10, 12 variables, it literally takes a computer, and that's the wonderful thing about these. If you know the basis of this understanding. Now, this is where it takes some time, but if we have a setup, which we do, now it's 2 by 2. If I have a 3 by 3, I got 3 equations, so that's 3 rows, and 3 variables, x, y, and z. And I could solve this right here. There's my 2x minus 3y plus 4z equals 91. 4x plus 7y plus 22z equals 201. 3x plus, that should be 8y. Now, I'm going to be consistent here. Make it 8z. We got 0 here. And equals 32. Now we had 2 by 2. How do I determine the determinant of a 3 by 3? Well, here's a 3 by 3. It is my A times my EFHI minus my B times my DFGI. See, this is getting messy here. And then times my C plus my DE and GH here. And then once we get that part, we just multiply times A times E times I minus A times F times H minus D times B times I. And you can see what's going on here. And really what we're doing is we are basically determining, trying to erase this here, what we did before when we switched to 2 by 2. We're doing the same thing, except for the 3 by 3. We're cutting across all of these right here. This one versus this one. And then this one versus, I think, this one. With every possible combination, that's what these are here. You say it's pretty hard, but it's not wonderfully nice on a Microsoft Excel. And I'll do a video of that to show how quickly it is you can do it in Excel. A 4x4 is even worse. You can see I've got four variables here. Here's how you find the determinant. And then actually this is the answer right here to get to it. 5x5 is even more cumbersome. See what you have to do here. I'm just showing you what you have to do this to get the determinant. And these take a long time. This will probably take about a day, I don't know, maybe 6, 7 hours to do. But it can be done instantaneously on a computer, which I'm going to show you in a separate video here. And that's why in the real world, if you understand how matrix algebra works, which I'm showing you here, the base of it, you can explain it to others. You just need to make sure you program it directly. So ultimately, you put in Excel, you got your A, that's your matrix. You've got your X, which remember is your X, Y, Z, or it could be A, B, C, D, E, F, G, X, Y, Z. And then you got your B, which is your result. That's all we're doing here. All of this, these determinants, is found by doing the what is 1 over that matrix of A. And obviously, the more rows and columns we have, the longer and harder it's going to be, but a computer can make it pretty quick and instantaneous. And an example here is I'm looking at, because I came from medical world, as you all know, the severity of disease spread, and nothing to do with epidemics, pandemics, or death rate to determine the overall global rate. And we could have several variables here. The vector, speed of the vector, and that's the vector in terms of the germ. What is it? But let's say it was salmonella or some bacteria or some virus. How long incubation time? That's another variable. I got those right here. The isolation time, how long it sits for you to start getting the symptoms at Z. How dense is the population? And then the average outdoor temperature. A lot of times, outdoor temperature means there's going to be more bugs, more insects, the warmer it is, and our people will also travel more frequently. And this is the number 2 killer of mankind. Number 1 is smallpox. Number 2 is measles. And these could be the equations for what the incubation time through the vector, isolation, population, average outdoor temperature is for 5 countries. And we can determine the rate, so these 5 countries, of what is the overall for global rate is. You can see I've just made this equation for, let's say, Uruguay, 3x plus 4y plus 8 plus, that should be Z, those actually should be Z's, plus 8Z plus 1045A plus 26B. And I've put this all here, and here's my answers, my result right there, to figure out what is the overall. Now, I said this is a 5x5 matrix here, 5 rows, 5 columns. And basically, we would have to find our 1 over, it is my A, 1 over that 5x5. I'm just going to put 5x5 here. And you saw in the previous slide how long it takes. But you can do that with a computer. Like I said, I'm going to show you. And you get these answers pretty quickly. And we use matrix algebra to determine them.